So hello everyone, and today I'd like to present to you this work in progress, which is an operating system for a ZAD based computer, right? And now I'll be completely honest, this is very bare bones. It's just a quick demo that I can do. So first of all, this is the whole thing with all of the programs that and all of the source code. And so if I do a quick make and I put my password in and then a make run, you can see this is the whole thing. So the kernel boots and the kernel then runs the shell, right? It executes the shell and then the shell repeats itself another 2 times and then it exits back to the kernel. And I can show you some of the source code. So first of all, let's look at the source code for the kernel. So kernel source kernel.c, and this is the thing, right? So this is the exec function, and it takes in a file name and it will read that file and put it at address, here it is, 5dc0. And this is also, if I do a vsplit, because I have just learned this command, so I can do open source kernel.h, actually kernel source kernel.h, and there we go. So you can see the transient program area, and this is from CPM. This is the same name they give the space where the programs are loaded. So the transient program area, and then the system call address, and this is a pointer which points to this function, right? So the idea is, and I will open a new tab, and I will open here the shell, the source shell.c, and here we go. So you can see we do some of this stuff. Now, to be honest, I'm not really sure what this line does, but it's there and it needs to be this way to function, right? So, but essentially what we're doing is we're getting a reference, I think, to this function right here, so that I can simply do a syscall with the system call number, or I guess, and the arguments, and then it will run from here. And okay, I wanted to say that at first I wanted to make this very Unix-like and only have these for reading. Like if I wanted to print something, I would just use the write syscall and write to like a file descriptor 0 or something, and it will print. But I think that's a bit complicated to actually do properly, so I'll leave that off, at least for now. I'm not sure if I'll ever get back to it, but in any case, here's the main function. I don't think I got here before, and what it's doing is it's loading this function as a pointer to that pointer, which is this right here, so that this program can call this function. And after that, it just prints a nice message formatted with color and blink information. We then get the fat info. So this is using fat16, and this is just a dummy function. If I do a tab new and I open from the kernel source file io.c, and this, a lot of this is AI generated, so I'm gonna have to look back at this, and I'll try to see if I can remove any variables and try to rewrite it myself so I can actually understand what I'm doing. But for now, it's just AI generated while I work on this. And this is what this function does. It doesn't actually read the MBR and give all of these, because this whole operating system is designed to work with these specific parameters. And this is because if we look in the bootloader section, so open bootloader source not ASM. So this is the first stage bootloader. And this is the part that's stored in the EEPROM at the beginning before we have any RAM available. So you're not going to see any call instructions because we do not have any RAM to have a stack to return to anything. And that's just what it is. But this, what it does is it initializes some devices. So for example, here it initializes the serial IO, and then it reads the second bootloader. Well, first of all, here there's a, I'm not sure if this works, I haven't tested this, but it first checks if I want to load through serial. If I want to load a second stage bootloader through serial, I can do so hopefully with this code. But if it fails, it's gonna go to ATA boot, to this subroutine, and it will start booting by reading the second sector. Yes, the sector 1, because the first one, 0, would be the MBR. So that's the second reserved sector, if that makes sense, where the code in the bootloader actually is stored. Now you could store the bootloader in the MBR, but you don't have as much space to do that, and I just don't want to mess with the MBR for now. So this is the first stage bootloader. After it's done, it will jump to I think address 512, right, minus, wait a second. No, but it should get to address 512 because that's where the second stage bootloader is. Now I'm not really sure what I've done here. I'll have to rethink this, but in any case, I'll open the second stage bootloader source. And this one, if I go to the top, you can see only, or actually put this in here. So only this specific configuration that you've seen, where was it? I closed the tab, but that specific configuration is the only one that works. And actually you can see some of this here. So the first fat sector, the first fat sector is sector number 2. So the first 0 is MBR, and then the second one is reserved for the bootloader, and then the third one, which is 2, if we do a 0, if we use 0 indexing, would be 2, and that's the, wait a second. Yes, that's the first sector where the fat actually is. So this already contains the first sector of the fat, if that makes sense. Then this is how many directory, root directory sectors there are, right? There's just 4. And how many sectors per fat there are, which is 127, and there are 2 fats. So 255. In any case, what this does is it looks for this file name in the root directory, and it will attempt to load it. This is also AI generated. This hexdump thing, I had it for debug purposes. But basically it just loads the kernel, right? But first of all, I forgot to mention this. This is loaded in the bottom 512 bytes of RAM, right? So the problem is that the kernel also has to live in this section of RAM. So to make this work, we relocate the bootloader in the beginning. So the first thing it does is this. Well, it first of all right here, entry. So it enters right here, it will jump to address 0, which it will start relocating itself, right? Will just copy itself to the top area of RAM, leaving some space for the stack, and then it will jump and execute everything else, which loads the kernel, of course, at address 0, and from there the kernel just loads the shell, and I've explained this already. There is some weird assembly that I had to mess with, because if I wanted this to work so that a process can exec another process and be replaced by that process, you sort of need this assembly to, first of all, save the stack pointer, to make it a clean, like to just save the stack pointer to have a return, to have something to return to that's a clean stack, right? Because this right here, when you do this syscall, it will immediately replace this program. The kernel will replace this program, and this program does not have time to return and clear the stack before getting back to the kernel. So the kernel has to sort of clean up the stack before, otherwise there's just the stack just grows, and at some point it ends. But with this you can have infinite, and I can actually change this. So if I just ignore this, this should just yes, it runs infinitely, because it just replaces the code, and the stack doesn't grow infinitely because it gets cleaned by the kernel, right? You can also change this to make it, and this is just a temporary variable, so that I can test write this ability, because I want it to end at some point, so it doesn't look bad on the terminal. But I think this is kind of all. It's very bare bones, but I think you can see where the idea is, and hopefully I'll keep on working on this and I won't lose motivation that easily. But for now, thanks for watching, and I'll see you next time.